We will begin the filter design with a technique called frequency sampling. So to this end, assume that we're about to design an FIR filter h of n of length n. So for an FIR filter, we know there is a relation between the discrete time Fourier transform and the discrete Fourier transform. So namely, the discrete Fourier transform at index k is a sampled version of the discrete time Fourier transform at the frequency given by nu is equal to k over n. So this suggests an idea for designing a filter. So suppose that we have a desired frequency response d of nu, and this could be the low-pass filter that we discussed earlier. And we select an appropriate filter length n, and we build a discrete Fourier transform h of k by sampling this desired frequency response at intervals given by k over n, where k ranges between 0 and n. And then we compute the inverse discrete Fourier transform of this discrete Fourier transform h of k in order to get back into the time domain and obtain our filter taps. So this procedure of designing the filter h of k has the property that by construction the discrete time Fourier transform of the filter h of n will satisfy the property that its frequency response h of nu is equal to the desired frequency response at every such sample point, which is given by k over n in terms of normalized frequency. So this is a way of matching a desired response for a finite set of points in the frequency domain. However, one thing to note with this approach is that if you just pick an arbitrary desired response, it's not necessarily guaranteed that this will yield a real valued h of n, let alone a linear phase filter h of n. So there is a number of standardized designs which add some structure to the desired response, which in turn will guarantee that we get the real valued response h of n and also satisfy this linear phase property. And we'll look at that next. So here we see such a design for a type 1 linear phase mth order FIR filter. So m here being the order of the filter implies that the length of the filter will be m plus 1. So we see that the desired response d of nu at the sample points k over n is specified in terms of its amplitude and its phase. And the phase is completely determined by the design, so there is no freedom here in choosing the phase, and this is in order to ensure the linear phase property in the end of the filter. But for the amplitude, all that we have to satisfy is this symmetry property, which has to do with the fact that the discrete time Fourier transform of a real valued signal has to be symmetric, so we have to satisfy such a symmetry property in the amplitude coefficient in order to maintain the real valuedness of h of n in the end. But we're free to choose a of k for k between 1 and m over 2. And this design here assumes that m is even, so m over 2 is an integer. Then we have a closed form formula for the impulse response in time, which looks like this. So the exact structure of this formula is not so important, but instead we can look at an example to see how this behaves in the frequency domain. So what we have here is an example of a design of a bandstop filter. So a bandstop filter is a filter which takes some set of frequencies, in this case between 2 over 10 and 3 over 10, and removes them. So the desired response would be this solid straight line which goes here. And what we can see from the design of the filter is that at the sample points with a spacing of 1 over n, or 1 over m plus 1 in this case, where m is the order of the filter, we have that the discrete time Fourier transform of our filter is identical to the desired response. And this is what this frequency sampling technique guarantees us in this case. And we've only shown the sample points up to a normalized frequency of 1 over 2. So since we're dealing with a real valued filter, the discrete time Fourier transform would be symmetric. So another set of frequency sample points would be given by this set of frequency sample points within this range. But these are the points that we are free to choose. And we also see some of the properties of the filter design based on frequency sampling. So for instance, while we guarantee that the response is identical to our desired response at the sample points, we have relatively little control over what happens to the response in between sample points. And in particular, for sample points close to this cutoff frequency of the filter that we're designing, we'll typically have these overshoots. So you'll have a large deviation in the designed frequency response from the desired frequency response. So one idea to address this would be to increase the order of the filter. So if we do that for this case, increasing the order from 20 to 30, we see that we will indeed get a larger number of sample points since we just increase the length of the filter and can therefore determine its value at a larger number of frequency sample points. However, we don't really address the fact that we have these variations close to the transition boundaries of the filter. And we can increase it even further to a 40th order filter, so a filter with 41 taps. And here we again see that we have these overshoots. So generally, we can make these overshoots more and more narrow as we increase the length of the filter, but we really can't address the magnitude of them with this response, or with this approach to filter design. So here we have the design for a type 2 linear phase mth order FIR filter. So being a type 2 filter, this implies that the order m is odd, so the number of taps in the filter is even, and it's a symmetric filter. So also here we see that the desired response d of ny is given at these sample points by an amplitude and a phase, and the phase is again completely determined by the design procedure. And also here we satisfy these symmetry properties for the amplitude sample points. But given that the number of taps in the filter is even, it means that we will have a tap corresponding to the frequency 1/2, and due to this symmetry property, this tap will have to be equal to 0 in order for this to work out. So which means that this design cannot be applied for a high-pass filter that should let through the highest frequency at 1/2, or for a bandstop filter which also should let through this frequency. Also here we have an explicit formula for the filter in the time domain, which isn't so important. It's just basically used in order to tabulate the filter in the time domain. And we can look at an example. So in this case, the design of a low-pass filter with a cutoff frequency of 2/10. So for this particular example, the order has been chosen to be equal to 21. So there are 22 taps in the filter, and we can see that we have one of the sample points identically at this frequency of 1/2. Also in this case, we see that we have these overshoots, and you can compute how large these are, and in this particular case there will be 15.7 dB below the pass band if you look at the ripples in the stop band of the low-pass filter. And as noted for the case of the type 1 filter design, also here for the case of the type 2 filter design, increasing the number of taps or the order of the filter will not greatly increase its ability to suppress frequencies in the stop band. So here we have a slight increase of 16.3 dB in the stop band, but increasing this even further doesn't necessarily further reduce this figure, but it could actually increase it depending on where the sample points end up. You can continue these designs also for type 3 and type 4 filters. So for a type 3 filter here, meaning that the order is even and we have an anti-symmetric response in the time domain, this would be the design. So the phase again would be determined by the design. We have a freedom to choose the amplitude. So for this particular case, we'll have to choose the amplitude corresponding to a normalized frequency of 0, as well as a normalized frequency of 1/2 equal to 0, which means that the only type of filter that we could implement with this approach would be a bandpass filter. And we could illustrate what it would look like in the frequency domain here for a case when the order is equal to 20, so we have 21 taps, and where we have designed a bandpass filter with a pass band between 2/10 and 3/10 in terms of normalized frequency. For the type 4 filter, we would be allowed to choose the amplitude in the following way, but we would need to require that the filter's impulse response or frequency response at frequencies equal to 0 is equal to 0, which means that we couldn't, with this approach, design low-pass filters or band-stop filters, since these would be, by definition, required to let this frequency through. And here is an example of what it could look like for a design of a type 4 filter, so M being odd here, so we have an even number of taps, and the filter design in the time domain would be an anti-symmetric design, since it's a type 4 filter. And here we have the frequency response of this design for a high-pass filter. So again, we see that we match the desired response for the sample points, but we will always have these overshoots in the filter. In all of these examples, we only looked at the frequency response h of ni for normalized frequencies ni in the range of 0 to 1/2. But what will it be for frequencies in the range -1/2 to 0? So will the frequencies at negative normalized frequencies be equal to a symmetric version of the frequencies at positive? Will it be equal to an anti-symmetric version? Will it be equal to a conjugate symmetric version? Or will it be an anti-symmetric conjugate version of the frequency response for the frequencies in the range 0 to 1/2? Well, the correct answer is option number 3. So since we're dealing with real-valued filters, we have this property that the discrete time Fourier transform of a real-valued sequence will always be conjugate symmetric around the normalized frequency of 0. So option number 3 is the correct answer. So far we looked at different recipes for designing different types of linear phase FIR filters. And one of the things all of these designs have had in common is that the sample points in the frequency domain have been uniformly spaced. However, we can also think of designs where we have a non-uniform spacing of the sample points in the frequency domain, and that can in some cases be beneficial. So let's exemplify that with the design of a type 1 FIR filter. So here we have the frequency response of this filter being given by the discrete time Fourier transform of the impulse response. So if we now assume that h of n is a type 1 filter, meaning that the order of the filter is even and that the impulse response is symmetric, then we can rewrite this equation in the following form, where we have the phase explicitly and the amplitude explicitly as two multiplicative terms. So the thing to note here is that in the amplitude of the frequency response, the filter taps in the time domain enter into this expression in a linear fashion. And what this means is that we can specify the amplitude response at a particular set of frequencies ni, and then solve for the impulse response through a set of linear system of a system of linear equations. So each particular frequency we specify would end up being one of the equations in that system of linear equations. So we can exemplify that in the design of a bandstop filter. So here we have a similar design problem that we had before with a bandstop filter, but now we placed the frequency sample points non-uniformly within the stop band here. And the thing about this design is that we can now increase the order of the design by placing one or several more sample points. So for instance, if we didn't like this overshoot at this particular frequency in the stop band, we could place a sample point there and force the filter to be identically equal to 0 at that point. And this would lead to a new design, which may have some other problems on its own, in that it has overshoots in other places where we didn't have them for the lower order design. But at least in principle, we could go on and now place more and more sample points, although this is hardly a foolproof method of designing a filter without overshoots. So essentially, when we try to bring the filter to the desired response at one particular frequency, we'll typically have it popping up with overshoots at different frequencies. So in the previous example, where we designed the type 1 FIR filter with unevenly spaced frequency sample points, how many frequency sample points can we actually specify if we're designing an mth order filter? So can we specify a total of m frequency sample points uniquely? Can we specify m plus 1 frequency sample points? Can we specify m over 2 frequency sample points? Or can we specify m over 2 plus 1 frequency sample points? The answer is option number 4. We can uniquely specify m over 2 plus 1 frequency sample points. And this is because we're dealing with the type 1 FIR filter. It has to be symmetric. So if it has order m, it has length n plus 1. So it's only m over 2 plus 1 taps that are unique. The rest are determined by the symmetry property. So If you're designing a system with a non-uniform sampling point, we said that we would design this system by solving a system of linear equation. So if you have m/2 plus 1 free variables in that system of linear equations, then you can have at most m/2 plus 1 equations in order for the system to be well defined and solvable. So this gives us the option number 4, m/2 plus 1. So to summarize, what we have seen is that a filter can be designed by specifying the requested frequency response at a finite number of points in the frequency domain, and this would lead to an FIR filter design. If we take appropriate care, we can also ensure that the final response of the filter in the time domain is real valued and that it has this linear phase property that could be beneficial in many applications. However, one of the drawbacks of this design method, as we saw, is that it's generally difficult to control the frequency in between the sample points. So even if we increase the number of sample points in order to try to control the frequency, we still have an increased number of gaps where the filter can behave badly, so to say. And this is one of the main reasons that this frequency sampling approach to filter design is not so widely used in practice. But there are other better methods, and we'll look at one of those methods next.